Hi everyone, it's Donny here, Innovation Fika, 2:30 p.m. You'll be seeing this at 2:30 p.m. It's not 2:30 p.m. now, it's like early in the morning, the day before, being recorded in San Francisco. But you know, Donny, Innovation Fika, every Wednesday, 2:30 p.m., LinkedIn and YouTube. Today I am in San Francisco with KTH, and 2 days of conferences on something called the Stockholm model. And one of the really cool cases that are here with us is a startup, a scale-up called Novatron, which is a fusion startup scale-up. And I'm here with Erik and Philip from Novatron. And as I always do, and how I always start, I always start by asking my guests, who are you and what do you do? So I'll ask both of you then, Erik and Philip, who are you and what do you do? You want to start, Philip?
I can start, absolutely. I'm Philip von Segebaden. I'm actually part-time at KTH, still Director of Development at KTH. But since January I'm part-time Director of Partnerships at Novatron as well.
Oh.
But I'm moving full-time to
Exciting, okay. And Erik?
Hello, yeah. Thanks for having me, Donny. I'm Erik Odén and I'm one of the founders of Novatron.
Yeah.
I have a background of dating innovators, I say. The last 25 years run into people with brilliant minds, many of them with a background from KTH, and help them build a company around their idea.
Cool.
And 3 years ago I had no idea what fusion was. Barely, I know. I mean, it's the process of the sun and the stars, but that's about it.
Yeah.
And I had no idea that one glass of water, actually it's just coffee in this one, but if this was water, and it is mainly water, if the hydrogen in that water was turned into energy by converting it through fusion to helium, it would be enough energy to power your whole life of electricity.
In that glass of water?
Yes.
But how, okay, before we go into Novatron then, let's do the basic
the fusion homework.
The fusion homework. What is fusion? I mean, fission and fusion, that's the two big things, right, in nuclear.
Yeah.
So what is, today we use fission for nuclear power plants.
Right.
And that's the bad stuff when it comes, you know, toxic waste and stuff.
Yeah.
But what is fusion? What is that?
I'll give it a try and you fill in. You're the expert here, right?
Shoot.
Okay. So fission, right. You
Yeah.
split atoms, right?
Yeah.
Fusion, as you can hear from the name, you fuse them.
Oh, okay.
So it's about bringing them together.
Yeah.
And when that happens, there's a lot of energy.
So you bring atoms together instead of splitting them.
Exactly.
And how do you do that? You just sort of go.
Okay, to do that, this happens all the time in the sun, in the stars.
Okay.
The reason why it happens there also is because you have so massive gravity.
Yeah.
So you know, in the core of the sun,
Yeah.
the pressure is so high that these atoms they have nowhere else to go. So that's what happens.
Okay. So that is actually the sun. That's what happens all the time with the sun.
Exactly.
Okay.
And the challenge then, of course, is to replicate this on Earth because we don't have that gravitational power. And also you need very high temperatures.
Okay.
So we need to somehow create conditions that will actually enable us to reach fusion.
Okay.
Yeah.
And that, but it feels like, but this has been going on for quite some time, trying to achieve fusion, right?
Yes, and the challenge is the conditions in the sun. Since the sun is so dense, it's huge.
Yeah.
And with gravity, you pull everything together.
Yeah.
So the temperature you need in the sun is about 15 million degrees.
15 million degrees
to get fusion, and then it happens.
Okay.
And so in the surface of the sun, it's just like 5 million degrees. It's in the center you have the fusion reaction.
Yeah.
And to do that on Earth, the conditions, we don't have the same density as in the center of the Earth,
No.
which means the center of the sun, which means that we need to have even higher temperatures. So
Yeah.
to do that on Earth, we need to have it about 150 million degrees.
But that's an enormous amount of degrees.
Yes. And what happens when you heat up light elements, like hydrogen that you have in water, and heat it up, and at a certain temperature, this gas will turn into something called plasma.
Yeah.
And then the electrons will separate from the nuclei, the core.
Yeah.
Which means that all the particles that builds up this plasma are either plus or minus. They cannot therefore be controlled with magnetic fields. So then we on Earth can create walls with magnetic fields to keep the plasma in place, because otherwise if you have a wall and it's 150 million degrees, it's going to be cooled down.
That's
It's
what I was
not good
thinking.
for the wall.
You can't just like have a furnace and heat it up. You can't sort of go on your stove from 12 on 1 to 3 foot and then go to 50 million degrees, because that would just sort of melt the whole. Everything would just evaporate.
Well, if the mass is so low, so nothing will happen. Actually, you can have 150 million degrees in your hand, because it's just so few atoms. So in a fusion device, it's just like a fraction of a gram.
At any given point, there won't be that too much mass in there.
No,
so,
okay.
Yeah.
I mean, and that's an interesting thing, though. How big do you envision a fusion reactor? Do you call them reactors as well?
Yes.
Yeah. How big would you envision a fusion reactor to be? To be able to handle this? I mean, do we even know that?
Yes, I mean, we can see that with the technology that Novatron is using.
Yes.
So we have drawn up a full-scale reactor that will produce enough energy to power all of Stockholm. 1.5 gigawatt, 4.5 gigawatt thermal. They give the heat to Stockholm and the electricity to Stockholm. And that will be the size of maybe 2/3 of a Forsmark power plant.
Which is a nuclear power plant.
Yeah.
Yeah,
2/3 of that size.
Because then, of course, you need also, the site technology around it. So it's not just a reactor you're talking about. So it's a system, of course. You need to transfer the heat. So it's bigger in like the total infrastructure.
Okay.
But still.
But it's very, very small compared to other ways to produce energy, because it's so energy dense.
Okay.
So that it's probably the most, as far as I know, the most energy effective way when it comes to footprint that we could know of.
Wow.
So.
Okay, but because the reason I'm asking about size is that there's this meta debate going on about like wind farms that don't look nice, and people, the whole thing. So if I'm thinking that fusion is great, but if it was like 5 football fields of
Right.
so but it's a small thing, it's a smaller thing. What about safety? I mean, nuclear is kind of dangerous, with.
That's the fine thing with fusion, that it's so much safer.
It's so much safer.
Absolutely. You don't have the same rates of radiation, not at all.
Okay.
So that's one thing.
But is there no radiation from fusion?
There is some radiation, but it's not nowhere near the extent of the fission.
No, okay.
So, and also the materials that get affected,
Yeah.
You can store them actually above ground, and they will be okay
So, but-
in 100 years instead of what is it now for fission?
Yes.
Hundreds of thousands of years.
So,
I
but
could comment this because the fuel is non-radioactive, and the ash, the end product, which is helium, is non-radioactive. So you have no radioactive key parts.
No.
And then if you use deuterium depends on what fuel you use. If there is one hydrogen isotope called tritium, which is has some radioactivity, but it's compared to uranium, it's very, very different. So the thing is, inside the reactor where you have all this activity, it will be bombarded by neutrons. And when a material gets bombarded by neutrons, it becomes slightly radioactive.
Okay.
So you need to store it for maybe, depending on what kind of material it is, maybe 30 years, maybe 100 years, but compared to 100 million years, it's a huge difference. And then it's safe.
Oh, so, but okay, so in my sort of mind now, I'm seeing like a smaller house into which I pour a glass of water, and then it powers Stockholm, and then out comes something else, which is not so dangerous. Is that
Helium
something
is
like that?
completely safe. It's an inert gas, so it's really, I mean, people breathe in helium and sound funny.
Yeah.
In that sense,
Okay, so you'll be powering Stockholm and make everybody sound funny.
Yeah, that's possible.
Okay, so this is
might be a
the
side effect.
okay, so this is by far the funniest energy
For sure.
source we
For
have.
sure.
Okay, for sure. By the way, everyone, ask all your questions about Fusion and Novatron in the comments, because both Erik and Philip have promised to follow up on this broadcast to make sure that if you have any questions, they'll answer them as well. And you can always, of course, connect to Erik on LinkedIn as well and get in touch with him. And okay, and I'm going to ask you something else now, because another thing that I've seen me going around is like this concept of antimatter. Has that got anything to do with fusion at all, or is that a completely different thing?
That's a completely different thing.
Okay. Do
You have no antimatter in the fusion we're working with.
But
it's clearly matter, and we're using actually, Einstein's
Yeah.
theory of where E equals mc
that one.
squared,
Yeah.
and that's how we produce energy.
Okay.
It's the mass of the two elements before fusing is slightly lighter than the combined mass of the helium that we create.
Yeah.
And there is actually, depending on what another neutron that pops away, but the combined mass of what's happening after is going to be less, and that mass is converted 100% into energy.
And I'm sorry for bringing up the whole sort of antimatter thing, but for me it was like sort of, well, that's something I've read about like in Superman and in like Marvel comics. But obviously there is something going on with antimatter as well.
I have another podcast, perfect topic, I guess.
Exactly. Okay, but that we can do it. If you're watching, I know who you are. I know who you are. But if you're watching and you want to do the antimatter one, let's do that one as well, because that could be a good follow-up for this one. But coming back then to Novatron, a lot of people have been trying to get fusion to work for many, many years. So what is the breakthrough that Novatron has done that will enable this now?
All right, so to create, as I mentioned, fusion on Earth, we need to create a magnetic bottle. And to create a magnetic bottle, you first need to create a micro-universe. So you need to create a space where there is nothing. So it's a vacuum chamber.
Yeah.
So we build a vacuum chamber, and inside there we put in a bunch of magnets. And when we power up the magnets, you will create magnetic fields that will create forces on anything that is charged.
Yeah.
And since the plasma is just a bunch of charged particles, if we put plasma in the center, inside where we have this magnet in this bottle, it will stay there. If they're confined in a way, so when a particle wants to move out the way, it's pushed back by the magnetic wall. And so far, the designers of magnetic walls have not been able to design magnetic walls so it doesn't leak on some spots. So there's always a weak spot on the previous solutions. And what Jan Jäderberg, the inventor of Novatron, came up is a solution that is stable, have stable magnetic walls everywhere in the space.
Right.
So which means that we can keep higher temperatures, the plasma at higher temperatures, and the plasma particles will stay longer, and therefore we increase the probability of reaching fusion. So we can work at higher temperatures at a longer time with a higher density, which is we come closer to the properties that you need to have like in the sun.
So regardless of what concept you are using, there are different concepts. This is the big challenge that is
So the actual stable magnetic walls is the breakthrough sort of leap.
I would say in this case the configuration is completely different than what anyone else has come up with so far. So that's the new take on this. And the thing is that it's been simulated now, I guess, millions of times. So in theory it works. Now we're going to build a prototype at KTH, at the LVN lab at KTH, to show that this actually works. It's being built this year, we're going to test it next year.
So you're actually testing the fusion prototype next year.
Next year at KTH. Can you imagine?
Wow.
And it will be the hottest place in Sweden.
150 million.
No. It will just be 1 million degrees to start out with, but
1 million degrees. And it will be
the hottest place in Sweden.
Hottest and happiest, because don't forget the okay, but then from there, I'm guessing it's not sort of a year until it starts producing energy. I mean, that's right. But how do you envision? I mean, how far away then to let's say, a commercial plant that powers Stockholm? I mean, when do you sort of see a possible date for that?
I think what's happening now in the fusion world, we've had these very large initiatives going on for decades, ITER and others, and it's always been a far off cry, right? But now what's happening, we have many private startups, or many, 30 in the world, something like that, going in the fast lane. So I think now that what we are saying and others are saying is that this time curve is starting to So instead of say 30 years, let's say 15.
Yeah.
Something like that. This is an approximate guess, of
Yes,
course. It depends on manufacturers. That's good.
They've asked everybody that works in these startups and that fill in this form and to ask when do you think we have fusion on the grid, and 93% of the people that work in that believe it's in the 30s or earlier.
Yeah.
So I mean we're talking very soon.
Yeah. Well, I mean, it comes to some kind of a point as well when it kind of an exponential development
Yeah,
as well.
exactly.
When it's like when the AI thing started going.
Yeah.
People said 2050, 2060, and then it was like, oops, 2040, oops,
Yeah.
2030, and then we're creeping closer and closer and closer to the whole.
I think a good analogy here is maybe the space industry, NASA, SpaceX, that kind of thing happening. That the technologies that come out now in these private companies, it rests upon all the fantastic breakthroughs that have been made. You know, we come a very long way since the 50s. There's a fraction still to solve, but we're getting.
But now it's more. But is there anything else missing in? Like we have like a puzzle here, right? We all need all of these pieces to get fusion achievable. Do you have all of like the pieces of the puzzles, and we just need to put them all together, sort of, or is it something? Oh, we're missing one piece that we still don't know how to do.
It's not a core piece, but still it's a lot of development that needs to be done. I mean, we're focusing on the confinement to put all these this plasma in a stable way inside this magnetic walls.
Yeah.
But you need to heat up. First you need to create the plasma and heat it up. You need to inject it. That needs to be to develop not only for research purposes but for continuous operation. You have the walls that's going to be bombarded with neutrons with high speed, and when they are slowed down, they will create a lot of heat, and so that bombardment will create a lot of strain on these walls. So what materials do you use for them to last better?
So there's things
challenges that we need to work with, and that's being done in these projects. But it's still it's a super system engineering challenge with a lot of different sub-challenges that need to be put together in a big system.
I mean, because we have a lot of viewers that are entrepreneurs, students, PhDs, also some researchers. We have lots of people watching this show. And so the question, so then if you were going to say something to people out there that are super interested in like joining the quest for achieving fusion, where would what would you want them to get into? Where could they sort of start in getting, because we're still like 15, 20 years away. I mean, we have, what can we do to help this happen then? Because you're doing your thing. What can anybody else do?
I think one thing, if you're a talented student today, and you're in this field, please continue. We will need, the competence. Especially in Sweden, I think there are other countries which are ahead of us. But I mean, this is going to happen. Fusion technology needs competence. So if you're interested.
So if you're into energy and sustainable energy, look into the fusion field. That's number one.
That's number one.
And any sort of other fields that could somebody please fix this for us? That would be great.
I mean, building a fusion power plant is it's architecture on the other side. It's all the energy aspects of getting the power out to the grid. It's all kinds of diagnostics to measure different parameters all over the place. There's going to be control systems. I mean, pretty much any field that you have. It's chemistry, it's material sciences. So I think
there's loads to be done.
Whatever you study, it's probably a room for you.
But this is cool though, because we're seeing so many new breakthroughs in technology. I mean, we're seeing new battery technology, we're seeing fusion, we're seeing aviation, we're seeing space, and all of these will need so many new competent people. There's so much to be done, people. There's so much to be done. This is, as you know, the world's fastest half an hour, and I haven't kept track of trying yet, but this has been so much fun. We're standing in a hotel lobby now, if you're wondering why all the noise is going on. I managed to catch Philip and Erik actually before breakfast here in San Francisco. So I'm super grateful for you giving me your time before breakfast.
Thanks, Tommy.
And as I said, post all your questions in the feed while you're watching this, because both Erik and Philip will be checking the feed. They might even be watching it live tomorrow morning, Wednesday, when you'll be watching it, 2:30 p.m. Wednesday. But for now, I'll say thank you to Philip.
Thank you.
I'll say thank you to Erik.
Thanks a lot.
And Novatron, is a website somewhere? Novatron?
NovatronFusion.com.
NovatronFusion.com. Follow that website and follow development. We are making it happen.
Fusion is happening, people.
Fusion is happening, people. Thank you so much. Bye, and I'll see you next week, 2:30 p.m. Innovation Fika. Thank you all.